Good morning, everybody. When I say good morning, sometimes I say that a bit ironically because it's evening. But right now, it is about as morning as it gets. It is 4:03 a.m., very early. I'm up. I got my cup of tea here. I don't know if you can see this, but it's actually like steaming. And, as usual, we have a Codeforces round. Let's go. Starts in 1 minute. It's Codeforces round. Let's see. 7:49. Div1 and Div2 combined, which means we'll have lots of problems. We're also a little bit more in the Halloween spirit here. The light and lamp. And hopefully this goes all right. I will be very try-hard mode on this contest, so commentary will be on the lighter side. But maybe not quite as non-existent as last time. And obviously the goal here is to do well here, get a positive rating change. This page is temporarily blocked. Mike, what have you done? Okay, maybe this is like very demanding, so they shut it off during the contest. I don't know. But yeah, anyway, the point of this is to indicate that past several rounds I have gone down in rating. Hopefully that won't be the case this time. We got some paper and a pen, some tea ready to go. Not some water though. Maybe that's the Galen Collins secret that I'm missing. Okay, let's jump into the contest here. N greater than 3 positive integers. Find the largest subset of the array such that the sum is a composite number. So it's either everything or we remove the smallest, or we remove the smallest odd. Well, the sum is all small. So it's everything. The size of the largest subset. Oh, the largest subset. So either it's n or n minus 1. Oh, and then we have to print it. What if they're multiple? I'll put any. Okay. So yeah. All right. So if this is a probable prime, then this out n. Okay, otherwise int odd index equals 0. If I is not equal to OI, then sys out I plus 1 plus a space, and then sys out. Okay, that should be good. Come on. Yeah, oh, first one's not right. A plus, oh, if not 2, 1, 3 should be good. Got A. Good. On to B. We want a tree with n nodes. We've asked our disciples to make the tree. However, we have m restrictions to make this tree as heavenly as possible. Ooh, that's hot. A tree with n nodes is a connected, undirected graph with n nodes and n minus 1 edges. Okay. We know what a tree is. Thank you. A restriction consists of 3 pairwise integers, a, b, and c. Signifies that node B cannot line the simple path between A and C. Help him Find heavenly trees for multiple sets of restrictions. Okay, so we only have m restrictions, which means there's one node that won't be in anything. So we make that the middle, make everything else a star. Yeah. Okay. Any other requirements? This can't be, yeah. They're distinct. And the only three, yeah, that's fine. Okay. Good. Yes, that's a legit construction. Okay. Int n equals this. Int n equals this. Why are we given m? Oh, m's the number of, yeah. Okay. Int center equals 0. Well, okay. Boolean array hit equals new Boolean array n. Hit at a at 1 minus 1 equals true. And then we need to print. So it's can we print these in either order? 7, 6, yeah, okay. So if I is not equal to center, then this out. How big can this be? Pretty big, so we need print writer. This out I plus 1 plus a space plus center plus 1. Okay, connect 7 to everything because it's never in the middle, right? And then, yeah, I guess let's just submit this. Let Codeforces check samples for us. Pretty confident with it. Consider a grid in which some cells are empty and some are filled. Call this grid exitable if, all right, we got it, nice. If starting at that cell, a cell is exitable if you can exit the grid by moving up and left through only empty cells. This includes the cell itself, so filled cells are not exitable. Note that you can exit the grid from any leftmost cell by going left and any topmost cell by going up. For a given grid, let's call a grid determinable. If given only which cells are exitable, we can exactly determine which cells are filled and which aren't. Interesting. Okay, you're given a grid of some dimensions. We need to answer Q queries. Each query gives us 2 integers. Wait, what did they say? There's an issue with the checker. Okay. Hopefully it's not letting everything pass when some things are wrong. Hopefully it's also not unrated. I guess we'll see. We're given a grid with some dimensions. Has it been 20 minutes already? No way. Oh, it's been 7. Okay. I thought this was a 2.5-hour contest, but we're given some grid. We need to answer some queries. Each query is given, okay. So we're given some range of columns. Interesting. That's a bit odd. It's a bit odd, but okay. So whether this is determinable. So if we're given these exit points, can we determine whether it works or not? So yeah, the question is just, do you have any like triangles with the top left filled? Well, basically, it's got to be, yeah, the set of exitable cells has to equal the set of filled in cells. Because if there is any cell that isn't exitable, you're screwed because you have no way of knowing. So 1 to 3 is, yeah, that's right. I guess, so this is the, you need something, or maybe it's just this. You just need x and then x to its top right. Yeah, because then this square's in trouble. I didn't get judgment failed, so it should be fine. Yeah, so we just find all illegal cells and then check if there are any in the range. And that should be good. So yeah, 1, 3, 3, 3 is fine. 4, 5, 1, 2, 3, 4, 5 is not. 5, 5 is. 1, 5 is not, yeah. Okay, awesome. Easy problem. We'll get this real quick. Int height equals this, width equals this. And then it's cumulative sum. So we have that. Now we have to figure out this illegals nonsense. Vote second thread for president 2020. I'm kidding. It's a joke. Don't be offended. It was literally a joke, and it was funny too. So if you're offended by that, you can get over it. It was funny. All right, so let's calculate this. So for int y equals 1, yeah, y is less than height, y plus. For int x equals 1, same width, x plus. If board at x minus 1, y equals capital, I think it's capital, and board at x, y minus 1 equals this, then illegals on x at x plus plus. And it is cumulative sum. Now we have our queries. So we don't count the first row, so this minus illegals on x at x2 plus 1. This is backwards. Rinse this out. Count equals 0. If it is, then yes, otherwise no. And then we probably need a current writer. Single test case. Nope, what's wrong here? YX. Gets me every time I try and be smart or be fast. Alright, should be fine. Not fine again. CS. Looks good. Yeah, just double check the logic in my head. Oh, come on. You can do this, Codeforces. You can do it. We'll read D while it's running, and then use our safe notifications. The meaning of life is a permutation, not the integer 42. Oh my goodness. My worldview has been shattered. Akmar, having created... Oh man, a very powerful guy. Okay, got it. Nice. We can figure out some of this permutation with some queries. A query consists of an array of integers between 1 and n. And A is not required to be a permutation. Oh, okay, so we have a permutation. Presumably we want to guess it. We give some array. Akmar will compute the first pairwise sum of A and P. The pairwise sum of A and P, meaning he will compute an array where S sub j equals the sum of elements for each thing. Yes. Then he will find the smallest index k, such that S sub k occurs more than once in S, and will answer with this index. The index that occurs more than once. If there's no such index k, he will tell us. We can perform at most 2 n queries. Find out the meaning of life P. So we're given some permutation, and we find the smallest index where S sub k occurs more than once. So take the first index, and subtract. So okay, let's find out what is the first index. What is 1 bigger than the first index, I guess? So let's call this 0, and then we want to find +1, and then +2, and then +3, and so on. And then we'll hit like some wrong answer thing. And then we want to find -1, -2, -3. So in total this will take n moves. Yeah, it'll take n queries. How do we find the +1? We make this be, how big can this be up to n? Yeah, we just do this as 1, and then everything else is 2. Or I guess we make this 2, everything else 1. That'll give us what is us +1. Yeah, okay. So that's the idea. Now we have to implement it, and yeah, let's use a scanner. All right, so we've got this array. Start by reading n. Good. Then we get to ask a bunch of queries. Okay. So so static int search for returns the index or -1 otherwise. So int x. If x is greater than 0, it's greater than 0. Oops, don't do that. Nope. Then we want to make the first thing bigger. We can't do that. Okay. I guess let's just do string builder. So then, yeah, sp.append x plus 1, and then for and I equals, we also need n, equals 1 less than n plus plus sp.append space and a 1. Okay, then print this. Otherwise, we do a similar thing. So we do, ooh, okay, so, well, is this going to be a problem? If x is equal to n, then return -1. If x is equal to -n, also return -1. Otherwise, we'll find it. Okay, so in this case, print this and then a 1. And then here we print plus x plus 1. And then our answer, I guess we need a static scanner. Our answer will be this -1. You can return that. Okay. So our index will be search for this target value, pass in n. If index is equal to -1, then break. Otherwise, it's not. So then we say real array at index equals target val. Then we continue, and then we do the same thing with target val starting at -1, decreasing forever. And we look for some stuff. Okay, so do we ever print something that's illegal? This needs to be -x because this will be negative. Wait, no? Yes. Yeah. And I think we're good there. So we should always print legal stuff. Now we have this array. So int min equals 0. Okay, and then for int I in real array. This out. We need to print an exclamation point first, then print I minus min plus 1 plus a space. This out. Okay, we should be good there. Let's try this real quick. So 5. We have a sample array that we're given. I guess let's do it. So let's say our permutation is 1, 4, 1, or 1, 4, 2, 5, 3. That's not a good example. Try again. 3, 1, 5, 4, 2. That's a good example. Okay. So if we add 2 to each number, if we add 2 to 3, it'd be the same as index 4, which is 1, 2, 3, 4. Okay, so index 4. What if we had 3? So then this is equal to 6. We add 1 to everything else, so then we get index 3. We can't, that is nothing. Negative, 0. And 0. Okay, what if we add, so now we're looking for the 2, so that's index 5, and then this is, we look for the 1. That's index 2. There are nothing there. 3, 1, 5, 4, 2. That's good. Oh no. That's an AC, ladies and gentlemen. Codeforces will let me submit. So we'll read E here. Q Tau, being the little prankster she is, has decided to scare you with a graph problem. We're given a connected undirected graph of M nodes and N edges. And then we have Q queries. Each query has 2 nodes, A and B. Initially, all edges in the graph have weight 0. Okay, so we're given, is it unweighted? Okay, so it's initially unweighted, but then it becomes weighted. Hello. What's up with the submission? Are we TLEing here? Wrong answer, pretest 1. For real. Why is that? What did I do wrong? I don't think so. Oh wait, what? What? Wait, what is the input? Oh, they give me the first index. Wait, what did they say? Maybe I misread this. I definitely misread the problem. Come on, give me the statement. Find the smallest index k such that sk occurs more than once in S. Okay. Yeah, so we're doing this all backwards now, aren't we? Yeah. Yeah, and then make this, and then, okay, so we put 1 at the back, fill in a bunch of stuff, make the bottom 0. I think this actually is just that easy. So 5. Okay, what is the first? Yeah, let's just submit this and then check it after. Come on, man. Okay. All right, so 5, we find the thing that is 1 more than 2. So this is position 1. And then it's 2 more than 2. It's position 4. And then that's a 5. So that is position 3. There, we don't have any of those. Oh no. Darn it. I'm gonna get it wrong. Yeah. One, 4, 3, 0. One, 4, 3, 0. I answered 0. Oh wait, 1, 4, 3, 0. Okay, so this is position 2 and 0. 3, 1, 5, 4, 2. Yes, it should be right then. Got it. All right. Thank you for letting me know. Moment of bloom. How are we doing, by the way? I feel like we're doing pretty well. Let's like stop and smell the roses here. 6th place. Screenshot. That's not bad. That's not bad. We're beating Omnic. Good Lord. All right. let's keep her moving. This tea is doing the trick. It's just lemon tea. Just the classic stuff. Hugh Tao, being a little prankster she is, has tried to scare you with this graph problem. You're given a connected, undirected graph, n nodes, m edges, with q queries. Each query is 2 nodes. Initially, all edges have weight 0. For each query, we must choose a simple path, starting at A, ending at B, then add 1 to every edge along this path. Determine if it's possible, after processing all q queries, for all edges in the graph to have an even weight. It's a graph? It is a graph. We can make it a tree, though. Yes, make it a tree. Why would we not make it a tree? Let's make it a tree. If it's not possible to determine the smallest number of extra queries we need to add to make it possible. Okay, suppose we have a graph with all even edges. If we have another edge in this graph, it connects 2 nodes of this tree, we just add it to the tree. So yeah, so we might as well just have a tree. There's no benefit to having a graph, so we just take an arbitrary spanning tree. Arbitrary. Is it arbitrary? Not necessarily. Yeah, the spanning tree we pick may be important. The spanning tree may indeed be important. Because you might have a case where choosing a better spanning tree might connect some odd paths. Right? You might have like yeah, the spanning tree is definitely relevant because we cannot choose this edge, instead choose this edge. Oh, but no, we can't. So the spanning tree might not even matter. Doesn't matter. Maybe it doesn't, because we can't connect this, because that would take 2 turns. So yeah, we might as well not. So I guess it doesn't matter. I don't think it matters. But n times q? Should this be n plus q? N times q. That's a clarification. NQ. Okay. Come on, we gotta. I think this is n times q, but it might be n plus q. Does it even matter? I don't know that it matters. It's possible for all edge weights to be even, print yes, followed by 2 q lines indicating the choice of path for each query. in the same order the queries are given. Oh, we have to actually print the path. Okay, so it is n times q. Yeah, it's not a typo. Okay, that was just a dumb clarification. Sorry. Oops. Well, you know, I didn't know. Okay, so yeah, otherwise I thought you would just print how many you add, indicating the path you would take. All right, let's what is this? Indicating the path you would take. Bruh, that's fair. Okay, that's fair. Yeah, that's. I deserved it. I deserved it. Yeah. That's the better read the problem carefully. Okay. Let's draw this case. So this thing with these paths. So we have 1 goes to 2 to 3. 3 goes to 5. 1 goes to 4. 6 to 1. Lots of things to 1. 5 to 6. And 4 to 5. So we'll ignore that edge. Then we increment 1 to 4. 5 to 1. And 4 to 5. Yeah. Okay. What is this? 2 nodes, 4 nodes, and 5 nodes? What the heck? 4 nodes, 5. Oh, this is a 6 to 5 edge. Yeah, well, it doesn't matter. Yeah. Okay. So guaranteed this is connected. Nope, don't bookmark this. Connected graph, okay. All right, good, so we've got one test case. And then probably want to just try and set here. We have N and M, yeah, and then disjoint set DJ is new disjoint set. Oh, we can do a naive BFS for each query. That's kind of nice, actually. I honestly kind of like that. Oh, we also have the edges. Yeah, is there a better way of doing this edge thing? So we want to know when a node has, I guess it's just how many nodes have an odd degree, have an odd number of edges, yeah. Okay, so this is a list of edges, and then we need node other. This should be fine. Zero less than n plus node that I is a new node. Good, and then go through each edge. So we want int first equals this, minus 1, second equals this minus 1. If bj.union first, second, then we need to add this edge. So edge e equals new edge from nodes at first to nodes at second, then first nodes at first dot add or dot agj dot add e. Same thing with nodes at second. And then we should be good with that. So we now have our disjoint set. Int nq equals 0 equals this with each query. Now we need to do this BFS. So int a equals this minus 1, b equals this minus 1. We want int dist, and then node array nodes. For node nn in nodes, and then dot dist equals -1. And then from dot dist equals 0. And then array dec of node nodes equals new, or I guess it's BFS. Making an array dec. Well, not BFS is empty. Then we want to say node next equals BFS.remove. For edge e and next.adjacent, node other will be e dot other pass in next. This gets me the thing I can reach. Okay, so we have where we are, we have where we can reach. If o dot distance is not equal to -1, continue. Otherwise, o dot distance equals next dot distance plus 1. And then it's probably helpful to have a from. So I guess we don't even really need dist anymore. All right. So I guess, yeah, this will be an edge from. Yeah, okay, then e from equals e. Okay, so we have this. Oh, we have to add this now. BFS.add. Oh. All right, so we got this. So now we do BFS nodes at A and then nodes. We should be fine there. Now we have to update this. So let's make a list of nodes we've taken. Yeah, so this is fine. Okay, so yeah. So taken in query at QQ equals new node array, b dot nodes at b dot distance plus 1. And then int index equals, I guess, nodes. Well, we can just do this. So node at equals nodes at b. Well, at's not equal to null. Then taken in query at QQ at dot dist equals at. And then at dot e from dot count plus plus, and then at equals at dot from. Okay, so we're good there. Now what? So we've done this. So now we just need to count the answer. So for node nn in nodes, int e count equals 0. So for edge e in nn dot adjacency. If e dot count mod 2 is not equal to 0, then e count plus plus. If e count mod, where's the mod button? Mod 2 is not equal to 0, then final ans plus plus. Final ans is equal to 0. Sys out yes. Wait, what is the question? Added queries, yeah, okay. Otherwise print this out no, right? Okay, so we also need a print writer here. Okay, we printed yes. Now we need to print the answers. So for int q equals 0, q is less than nq, q plus plus. This out taken in query at q dot length. Normal out, and then for node nn in taken at query at q. Darn it, we need the ID. Taken at query. What's wrong with this? Taken in query. Yeah, out dot print nn dot ID plus a space plus 1, and then out dot print line. Hello. -1. -1 bfs.add from. Yes to 1 to 4 looks good. 4, 5, 3, 2, 2, 1. That doesn't seem right. Okay, let's try again. We have 6 nodes. We have the nodes 1, 2, 3, 4, 5, 6. Okay. 1 to 2, 2 to 3, 3 to 5, 1 to 4, 1 to 6, 5 to 6, 4 to 5. Okay, so it is kind of wacky. So we connect 1 to 4. Good. We connect 5, 3, 2, 1. 5, 3, 2, 1. Okay, and then we connect 4, 1, 2, 3, 5. Yeah, okay. No 4. Graph in the second test case looks like this. Oh, over 2. Yeah, it won't be. That's fine. Okay. Submit E. And then I guess we will, well, I guess we'll give it a minute here. Nice. What was the time limit on this? Thank you for not making it 1 second, authors. You did a good job. You earned your pay. 1 second time limits need to just, nah, not a thing anymore. Also, the fact that, can you submit in C++ 20 or whatever? Oh God, that's scary. Oh boy, this is gonna be brutal. Watch out. Don't think it was tested on that. Okay, anyway, on problem F. So how are the standings looking? We're not doing too bad. 10th place after solving E is really, I can't complain. For it being before 5 a.m., you know, it's a good day so far. It's not a bad day. It's not a bad day. F is the next most solved thing, so we'll go after that. Defender of childhood dreams. You find yourself playing with something, again in the city of something. Let me try this. Playing with Tusser again in the city of Layu. You know what would be brutal? If they made these names like something inappropriate but spelled differently, so you like accidentally say something bad. Like a classic D's nuts example, something like that. Or you name the thing something where you'd pronounce it and then it'd be something you couldn't say. And I'd have to go like edit this part out of the video. Oh, that would be obnoxious. Thank you for not doing that. As you take the eccentric little kid around, you notice something interesting about the structure of the city. That your back hurts. Something about the structure of the city. It can be represented as a directed graph of n nodes, labeled 1 to n. There's a directed edge from A to B. Ooh, if and only if A is less than B. That's a very interesting city. Okay, so you can go from anything directly to anything bigger than you. Okay, a path between A and B is defined as a sequence of edges, such that if you start at A, travel along these edges in the corresponding direction and end at B. The total length of the path is defined by the number of edges. A rainbow path of length x exists. A rainbow path of length x is defined as a path in the graph such that there exists at least two distinct colors in the set of x edges. It's a very liberal definition of a rainbow. You know, usually rainbows contain at least like 5 colors, but at least 2. Okay, you have 2 different colors along this path. Gotcha. Of x edges. Makes sense. You have a favorite number of k. You're considering the following scenario. If you were to label each edge with a color, what is the minimum number of colors needed to ensure that all paths of length k or longer are rainbow paths? That is a good question, my friend. K is at least 2. So you can definitely do it with n minus 1. Yes, you can always do it with n minus 1. Do you not want to just color the first n minus 1 nodes always? Why would you not? Sounds like an n squared dp. Because if you go to the end, length k or longer, yeah, so you need some like dp at your position, and then like the length. So it's going to be an n times k dp with like a fast transition. That's where this is going, undoubtedly. So how do we actually get it to work? I don't know. This geometry, colored tiles. Wait, is this the entire set? We have 3 more problems after this? Man, if you have no geometry in this entire set, you're not going to be 1 geometry. N by N grid, probably not flow. Lots of queries. N minus, so a tree problem. Not sure what this happens. Okay, some sort of math though. This is a good set. I mean, I'm kind of biased because I'm crushing it, but other than that, I don't mind the set. Okay. So G has a solve. G is the math one, so we're staying as far away from that as possible. And it looks like people who are good aren't really struggling with F. Yeah, it's a solve rate of about times 5, so about as expected. Looks like almost a perfect difficulty curve too. So far anyway. So great job on the set, whoever wrote it. I guess I'll have to read after. But nice set. All the problems are interesting. They're all good. They're all easy to read. I like it. Okay, how do we do it? Yeah, so if we're at some node, we want to know what can we force? Can you binary search the answer? Well, maybe it's not necessary. Yeah, so surely, is that true? Okay, so you've got your last node. Let's do this in a smaller marker. You have your last node. Then for the node before it, well, you just color this whatever. So this is colored 0. Okay, then the node before that. You can go here, or you can go here. Let's say k equals 2. Well, I guess if k equals... Would you, okay, so is it true you want to color the nodes and not the edges? All paths of length 3. 0, 1, 2, 3, 4. Can we color the nodes 2 different colors? Yeah, we can color the last 3 nodes a different color. Okay, that's not helpful. What about this? 5, all things of length 2. Then we have to color, we have to use 3 paths. So you can only allow things of length 1. So you can color, these 2 are length 1, these 2 are length 2, this is length 3. Eight things, you can let paths of length up to 7. Takes 2 colors. Does it? Okay. Okay, so the question is, come up with an example in which you can do better than, what is it, n, so we can use a path of, wait, is it of length, we can use a path of length k, n over k is c length. Yeah, can you ever do better than n over k? Ooh, I could make a hard call out of no. And then I get it wrong, and then it's okay, time to write the DP. So 11 corrects. How many wrongs? 3. How quick are the corrects? This took 11 minutes. When it took him 7 minutes to get E. This took 20 minutes. This took 15. So, okay, is it ever beneficial to have two different colored edges leaving some node? I think it just makes your life harder, right? Probably. I don't know, we can try it real quick. I don't know if it's correct, but is it right? Yeah, I have no idea. Let's try it. What are the odds this passes? 1 in 5. There's a 20% chance this is right. It wouldn't be this far back in the set if it were correct. Like, it's correct for samples, but it's not gonna be, that's also not right. What the heck? Wait a minute, what? I guess we only need to color 4 of the nodes, huh? No. 1, 2. Yeah. Greater than or equal to k. Then it's 2, it's got to switch every time. Yeah. One, 2, 3, 4. 1, 2, 3. Yeah, 2 and 2. Okay. And then. Whoa. 5, 2. Okay. There you go. Second case. Why is this? 5, 2. Tell me it only takes 3 colors. Why is that? Okay. All right. So yeah, we're in the 80%. So why is this 8 colors? 5, 4, 3, 2, 1. So we don't have to worry about the 1. This is going to be color 1 right here. Anything that can reach color 2 needs to have at least color 2. So this needs to be color 2. 4 can reach 2, or it can reach 3, or it can reach 1. So if it reaches 1, we can color this color 1, that's fine. What if it reaches 2? If it reaches 2, I guess we have to color 2. What do we color this? I guess we color 2, because why not? So this uses a 2 for everything. This uses a 1, so this just uses a 1. 3 uses a 2. 4 uses, well, we don't do that yet. We don't really care about that yet. So this has to use a 2. And for the 3, we have to use 1. And for this, we can use a 1. That's fine. Okay, so that's how you do it with 3 colors. Is there a better way? Not an obvious one. Yeah, so if you know everything ahead of you, you need like the max, I guess. Maybe the max. So 1 is just empty. 2 we'll use just a 1. 3 we can't use a 1 because it's taken. Oh, but this is like annoying. Because once paths get longer than 2, we're going to need something more complicated. Let's do it for 2 first. 3 uses 2. So 4, it hits 1. Oh, it's going to be logarithmic? For 2 anyway. And 2 is the worst case. Yeah, so probably anyway. Maybe, I guess we'll see. So this uses 1 and it uses 2. So it hits both of these. Yeah, so you can get a path of length 1, a path of length 2. Alright, what about 5? 5 has to reach 4, and 4 can have 1 or 2. So 5 needs a new thing, so 3. What about 6? 6 can hit 5, in which case it has to use something that's not 3. So we might as well use 1. Oh, but to everything else we can use a 3. Yeah. So then we use a 3 for all of these. So it uses a 3, and then it also uses a 1. So we can effectively double it. Yeah, okay. So it grows logarithmically. I guess it might be interesting. Also, thank you for the good samples, problem writers. That was good. It might be interesting, like, do we just want to make cutoffs? Like, turn the path length into length 2? Maybe. So we've got node 1, we have node 2. Let's have this color 1. Node 3, let's have this also color 1. Node 4, this needs to be colored 2. Yeah, so we leave this with 1. We leave 3 with 1. 4 we have to leave with 2. 2? Not with 4. Node 5, if we go to 4, we could use color 1, I suppose. Because with 4, we always leave it using colored 2. Nah, but that would be annoying. Or would it? We leave 4 with colored 2, so we might as well hit this with color 2. Then we don't have to worry about any of the 1s. Okay. Okay, then what about node 6? 6 would use 1 for 5 and 4, and then 2 for 3 and 1. So this would use 1, or it would use 2. So we're fine there, but we have a problem with 7. So when 7 hits 6, there's a path of length 1. Oh wait, that's fine though, because then it'll switch. Yeah, 7 can do 1 and 2 as well, because we have a path to length 6, and then after that it switches. In fact, we have multiple choices in this case. For 6, we can do a lot of things. In fact. Maybe we don't even need a DP. Maybe just the greedy works? This better greedy works? Possibly. They don't give us really any cases otherwise. How big is 7 choose 2? 8 choose 2. Why do I need a calculator for this? Is this really 28 things? Maybe. Yeah, we really can't brute force this very easily. So we have it solved for small cases. What is happening here? I thought I had caret installed. Do I not? Can we, like, what's going on with this? Just go. Caret, what are you doing? Do your job, Caret. That's not doing its job. What about CF predictor? Maybe it's Codeforces doing something wacky with its API, like blocking them. Okay, Cyan. This guy a cheater? Possibly, or maybe just smart. Probably just smart. Okay, yeah. Well, A through E were all easy, so. Okay, so. Okay, do I even have an algorithm here to implement? I guess I didn't go very high in this one. Okay, so I guess this is the same thing, but 4 is the end now, and now we have 3 things. Yeah. Yeah, so to 4 and smaller, you just use 3. So this is just a 3 boundary. I think this is like pretty maximal. So I think this is legit. How do we implement this? Wait, this isn't F. Okay, this is F. Wrong. Solve to int x into n colors. Yeah, let's get a bigger sheet of paper here. So we have this, then we have this. So this is color 1, this is color 2, and then we have this is 1 and 2, and then this is color 3, and then we have 1 and 3, and then we would have 2 and 3, and then we have 1, 2, 3, and then we have 4. Okay, so 3 is in. Is this just the, oh my goodness, is this the binary representation? So 0, 1, oh my goodness, oh my goodness. That is genius. So cool. Okay, it is just the binary representation. That's the colors it uses. And then what, when it goes to something, it uses the bit that changes, the least significant bit that changes. This is, dude, is this awesome or what? I'd like to see a proof of why this happens, but this is monstrous. Okay, 2 to 1, the 2-bit changes. Oh my goodness, that's it. The most significant bit that changes. Yeah. MSB that changes. Okay. That is epic. That is so epic. That is epic. Oh my goodness, that's so cool. Can we do better? So this is with 2 things. If the length can be longer, do we just extend? Yeah, we can definitely do at least a little better. Like, we can do better by a constant factor. This is worth trying, though. This is like, we've now reached the bar where it's hard enough that it, in theory, might be right. If I'm having a good day. Yeah, so we can make, well, last thing's got to be on its own. And then you do 2 things in this bucket. So you add a length of 1. And then you do 2 things in this bucket. But it'll change between buckets. Yeah, could you do better though? Possibly. Well, we'll try it. Let's just implement this anyway. Enter A. Enter A N. Yeah, I'll just do the, well, I guess I can't. Yeah, I'll just do this in reverse order. Okay, so now color from, okay, yeah. Color at ij equals I XOR j, integer dot highest one bit of this, and then integer dot number of trailing zeros of this. So we go for position 0, I is less than n, I plus plus. Yeah, what if it's all 3s? If we have things within a group, you can possibly change every time within that too. I'm not convinced this is right. If we have 10 colors, we just make a group of size 10 that's like not great. We're really just gonna let them just like waltz through without changing colors this whole way for free? Seems a bit generous of us, isn't it? I guess we can try just finishing the code and then thinking some more. Doesn't seem right though. Yeah. I guess let's just finish it. So bucket counter plus plus, if bucket counter is greater than or equal to k minus 1, greater than or equal to k, bucket counter equals 1, and bucket in plus plus, and bucket at I equals bucket in. Yeah, so now it's sysout array stack2string bucket. Oh, this needs to go backwards. So this is n-1. Or wait, is it? Yeah, let's just do forward and then reverse at the end. Okay, so 5.2, we'll just have that, okay. 10.3, we'll have 0, 1, 1, 2, 2, 3, 3. Okay, 10.4. Yeah, that's right, okay. This is log base 2. Yeah. Log base 2 over 2 is bigger than log base 3. Wait, is that true? That's not true. Yeah, log of n over 2. Okay. So that's 18. This is way smaller. That's 12. So this answer is going to be wrong, is what we're getting at. It's not going to be good enough. Yeah, it's wrong. I know it's wrong. Why bother submitting? I can feel it in my bones. This is not the best way of doing it. So, okay. So this is 1. This is also 1, right? Why not? So then when you have this has got to be a 2, but this could be a 1. But you might as well just make it a 2. Because if you make it a 1, you just make it harder for yourself later on. Yeah, so you might as well just make it a 2. What about this? So you can just make it a 2, because it's easy. Anything earlier, yeah, you just make this all a 2. So now you have a 1 and a 2 for this part. Can you do better? Well, you can't there. What about when you have a 1 and a 2? Maybe this is the best? I don't know. Dude, I don't know. Let's just solve this. Okay, n buckets. What is this? We don't even use x. Solve n buckets. What about 2 things within the same bucket? We can use whatever we want. Can use whatever we want? No, we can't. Yeah, so if you go from this to this, if you have a 2 here, if you use a 2, then you have a 2 here, then you're in trouble. Because you've got this. So, oh, it can just be, can it be any one of your outgoing edges? Yeah, because you can't have the same outgoing edge twice. So it's any one of your outgoing edges. Yeah, because you just, yeah. All right. Well, any one of your outgoing edges is just your highest 1 bit. Yeah. Okay, so int from equals n, from n minus 1, from 0 equals 0, from minus minus, int 2 equals n minus, or from minus 1, 2 is greater than or equals 0, 2 minus minus. If buckets, or if bucket at from equals bucket at 2, yeah, then int val equals integer dot highest 1 bit from, and then integer dot number of trailing zeros. And then sys out val plus a space, else int val equals equals ants at, ooh, this is not right. So this is a bucket at from. So then this is ants, or this is, yeah, ants at bucket at from to ants at bucket at 2. You don't need this ants. We should always use that, so that's fine. We use this many colors. Val plus 1, val plus 1. Okay, why is this? Colored IJ. Why is max due to 0? Oh, we don't have to, okay. Two. Yeah, I guess that's fine. 3. 2. 2. I think that's fine, okay. So, who's ready for this wrong answer? I sure am. Raise your hand. Test 4, test 8, test 8. 8's my bet. Wrong answer, pretest 8. Oh, 5. Not even 8. Okay, so that means you can do better when n is bigger than 2. Which makes a lot of sense. We are not quite optimal. Oh, the real question is it that we're not optimal or is it that we're illegal? I think I have a proof that we're legal, but that doesn't necessarily mean much. Do we give up this problem? Maybe. It's gonna be a tough one for ratings, that's for sure. Geothermal's getting this many wrong answers on E, which is really not that bad. I guess we'll read G. Needs to complete n tasks. He doesn't know when he needs to complete the tasks. Initially time is 0. Time travel happens according to the following rules. For each k, he will realize at time bk that he was supposed to complete the kth task at time a, which was earlier than now. Okay. When he realizes this, if the kth task was already completed in time a, he keeps the usual flow of time. Otherwise, he travels back to time ak. If he needs to travel to time ak, all tasks after this time will become incomplete again. That is, for every I, ai greater than ak. What is for every ai? AI will become incomplete. Oh, for every I, if AI. Is AI when he completes it? Probably. Oh, yeah, okay. Gotcha. He has a bad memory, so he can only time travel to AK only immediately after getting to time BK. What does this mean? Please refer to the notes for an example of time traveling. Let's refer to the notes. All tasks need to be completed in order for a funny scene to occur. What is a funny scene? There's a certain set S of tasks such that at the first moment all the tasks S are simultaneously completed. A funny scene will take place. There's a certain set S of tasks such that the first moment after all tasks in S are simultaneously completed, a funny scene will take place. He loves the scene and wants to know how many times will time travel before the scene takes place. What the heck? So when is this set of tasks complete? The set of tasks. So he gets the time when he needs to complete this task. What is BK? What is BK? And the time he realizes that he needs to complete it. All two ends of these times are distinct. Okay, so you are flowing through time, and it's like, oh shoot, I need to go do this. So he goes back to this time and does it. Oh, so you might realize something multiple times. Got it. So it's like you go to B, and then you jump back in time, and you do this thing. Okay. There's a certain set S of tasks such that the first moment all of the tasks are successfully completed, are all simultaneously completed, a funny scene will take place. So how many times do you have to time travel before such a case? Interesting. Okay, so you need 2, 4, and 6. 2, 4, and 6. So yeah, if you have like a thing and then something within you, you can just calculate that. The interesting part is like when you have something and then something that leaves your part, then it's like, okay, that thing gets modified. Or I guess it doesn't really matter. If something leaves you once you enter it, oh, it does matter. Also, when you come back to this, there's only some subset of things that need to be redone. But it does seem like a segment tree problem. It doesn't seem too hard. Ah, but I only have 33 minutes. Scoreboard tells a very seriously different story. Scoreboard says go for F and drop G. You're not smart enough. Alright, scoreboard, I'll listen. For now, anyway. So how do you do better than this? Our problem is we are not doing much with our lives when k is bigger than 2. We're just saying you might as well just go to the case when k equals 2, but you can probably do log base. So I guess what is the first example where they differ? So in binary we have the numbers 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. Okay. What about in base 3? We have 0, 1, 2, 10, 11, 12, 20, 21, 22. So this is 1, 2, 3, 4 nodes. We have to use 1, then we have to use 2. Wait. Wait a minute. Yeah, we have to use this. This uses 3. Okay, this numbering is off. Try again. So we have 0, and then we have 1, 2, and then we have 10, 11, 12, 21, or 12, 20, 21, 22. So this still should be better, right? We should be able to use 2, but we use a third for this. So 0, 1, 2, 1, 2. So we can do 5 nodes with without anything better. Oh, it's more than that. Whoa, it's way more than that. It's 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes. 9 is the best break case. Oh, that's obnoxious. Okay, 9 nodes, huh? Within each thing, we have a 0. Then to cross things, we have a 1. Yeah, because you can only be within each group. That's easy. Oh, that's so easy. That's so easy. I don't know how I don't see this stuff. Like it. Okay, I'm an idiot. So we've accomplished that, David. Now, what do we do with our life? Okay. Yeah, so it's like the same, kind of, but stop being hacky, I think is the goal. So we just need to make a number in base k. You know, I saw this, I'm like, the answer, it's going to be log base 3. This isn't log base 3, this is log base 2 of n over 2, which is not log base 3, and then I'm like, I'm going to submit it anyway. Okay, alright. At least I figured out the answer, or what might be the answer. Probably the answer to test case 5 anyway. Yeah, does this work? Yes, of course it works. Why am I even considering this? So we want the, just like the value in base. So I can just do integer dot. Can I, what is integer dot? Radix. How big can radix be? Probably not that big. Okay. Okay, so static int array in base. Yeah, maybe just a Boolean array. Boolean array. How big does n get? N goes up to 1,000, so this will be 12 big. All right. Oh, this needs to be an int array. Okay, fine. Okay, so int exponent equals 0, while x is not equal to 0, then to return at x plus plus equals x modulo k. And then k plus plus? No. And x divided by equals k. And then return to return. Base k at I equals equals solve of I and k. Nope, equals in base. All right, cool. First diff. So 4 int I equals 11. Is greater than or equal to 0. I minus minus. If this is base 0, this is base 1. Yeah. So if what do we print here? We print just the base. It differs in, yeah. Yeah, okay. So if what am I saying? If value in base k at ai is not equal to value in base k at ei, then return I. So otherwise, we don't need any of these bucket shenanigans. This is going to be pretty easy. What's wrong with this? Oh. Yeah, so ants equals new enter an, and then for int from equals n minus 1, from is greater than or equal to 0, from minus minus. 2 equals from minus 1, 2 is greater than or equal to 0, 2 minus minus. Yeah, so then ants at from 2 will be simply, we don't need any of this. This will be the first diff between from and 2. And then this will just be out.print ants at from 2 plus a space. I think we're good. First diff, calculate in base, and then we're fine. Yeah. Easy problem. Really? Why is that? so let's validate this really quickly. So we have 1, 2, 3, 4, 5. Good morning. That's when I usually wake up. 6 a.m. How much time do we have left, by the way? 20 minutes are fine. So this is, so we have, how do things get grouped? We've got these differ in the lowest bit, these differ in the lowest bit, these differ in the next lowest bit, and then this is the next chunk. So yeah, so 3, 3, 3, 3. Good. 1, 2, 2, 2, 2, 1. Yeah, that's fine. Let's go. How are we doing? Not bad. Not bad at all. I am relatively happy with this performance, to be honest. Are you not getting these? Is this FFT? You can do it, man. Okay, so my friends have H, which makes sense because G is a math problem. So I'm going to do H. Akmar is hosting, I'm not going to do H. Who am I kidding? I can't do H in 19 minutes, but we can give it a shot. There are N cities in Akmar land, Amkar land. Rather curiously, N-1 bidirectional roads connecting the cities together. It's guaranteed that you can reach, okay, so we have a tree. Each city has an enjoyment value E. Each road has capacity C, denoting the maximum number of vehicles that can be on it, and an associated toll T. So we have a tree, no, a city. No, we have, okay, we have a tree where the nodes have enjoyments and the roads have capacity and tolls. Okay, if a vehicle travels along multiple roads, they only pay the highest toll of any single road. So they play max, okay. So we have like max tolls, we have capacities, and we have enjoyment values, okay. Akmar has decided to host Q tour groups. Each tour group consists of V vehicles and a starting city X. Keep in mind that a tour group with V vehicles can only travel on roads with capacity greater than or equal to V. Okay, yeah. Alright, but you have in a full group at once, okay. Being the tour organizer, he wants the groups to have as much fun as they possibly can, but he must reimburse his groups for the tolls that they have to pay. Thus, for each group, he wants to know two things. First, what is the enjoyment value of city Y? Or what is, yeah, so what the maximum enjoyment value the tour guide can reach from the starting city. And second, how much per vehicle will Amkar have to pay to reimburse the entire group from their trip to X to Y? Are all enjoyment values unique? And integers unique? Not necessarily. Okay, that's kind of annoying. How much per vehicle will Amkar have to pay to reimburse the entire group for their trip from X to Y? Will always be on the shortest path. In case there are multiple with maximum enjoyment values, choose the one which they want to go to. Therefore, he wants to know the amount of money he guarantee. Okay, so they're going to go to the worst one, the most costly to him, and he wants to know of all of the things with maximum cost, which one has like a max edge query. That's kind of annoying. Yeah, that makes it tricky. So we can like add edges into the tree over time, maybe. But then we have, yeah, this is a pretty easy problem. Like this is an easy link cut tree problem if these were unique, right? Yeah, easy, very easy. It's simply add edges. You don't even need cut. It's just link and then range query, because you know the max in the component from a disjoint set. Yeah. Yeah. So it's simply, you don't even need a, yeah, you don't even need a link cut tree. You don't even, because you can just have the full static tree and then just do the query. So you have the maximum thing. The question is just like which things are maximal in this component. But really, you always have, like if you have a set of maximal items in their like meta tree, you always have everything there. Yeah. So like if you know the max, like these set of maximal things will make some meta tree. And like the sub tree sort of thing of your tree, but like a subset of nodes. Like a connected subset. They make it connected. They have a meta tree. I don't know what this is called. There's some name for it. The Cactal has a nice way of getting. But you have this like meta tree, which is like a tree embedded in your tree. And anything in this tree you can always reach, no matter what the query point is. Then when you add a new node, you might delete this entire meta tree, or you might add an additional path on the meta tree, which can be an arbitrary path. It shouldn't matter. Yes, so it's like an arbitrary path inclusion. Yes. So this is, ooh, we got this. We got it. We got it. Yeah, it doesn't matter which one you're on. I know how to do this problem, but I don't have enough time. Oh man, this is actually such a cool problem though. I'm just slow. I guess I was just slow with the last problem. Man, this whole thing came down to me doing a wrong answer on problem F. Was it F? Yeah. The wrong idea on problem F is just going to be so costly. I could have gotten problem G. Yeah, there's no way I can implement this in 10 minutes. I need a little bit of prep. I need like 5 minutes of prep, and then maybe I need like 3 minutes of prep, but then after that, I'm going to need a good 15 minutes to code it, which I don't have. Yeah, so you need like, do I need link cut tree or HLD? Let's do link cut tree. So I need link cut tree. I need range, range include. I need range include. I need range max. And then I need like range max with included. Oh, I also need range exclude. So yeah, range include, I guess let's just do range like multiplier plus equals 1. Range query min multiplier, and then like range sum with min multiplier. Yeah, so there's no way I get this. Man, is this problem? This is H too. It's H. Oh my goodness. It's problem H. How many? 3,500 points, dude. That were mine for the taking. I could have been in like 15th place here. Oh my goodness. I can do H. I can do H. H is not even that hard of a problem. It's just you need link cut trees and some time to implement it. You need a good 20 minutes to code it. It's easy though. I think. I could be wrong. Yeah. I guess we might as well talk about solutions. Because I don't have anything better to do. Okay. we still recording here? We are. Look at that. It's kind of surprising. All right. Looks good. 6:10 a.m. The day is just getting started. Let's do solutions here. Okay. Give me some free space, please. Okay. Yeah. So we'll go through the solutions to most problems. I actually did pretty well in this contest. So I know how to do A, B, C, D, E, F, and H. Let's go through solutions. So problem A. Yeah, so you're given a bunch of numbers, and you want to find the biggest subset of them that sum to some prime number. So this problem, ooh, crap. Crap, am I getting hacked? Oh, crap. Oh, shoot. 2 is prime. Oh, and distinct. Do I break? You can't have 2 things that add up to 2. Oh, good. Whew, almost. There was a case I didn't think about there. Okay. A little nervous. All right. So here's why my solution works. You have n distinct integers. So you have a bunch of distinct integers, and these add up to some number. And you want to pick as many of them as possible, such that if you add up all of these, they add up to some prime number. So they add up to a composite number. So the key observation here is that except for the number 2, all even numbers are composite. So what this means is if your array has all even numbers, the sum will be composite. Otherwise, if your sum is odd, that means that it has at least one odd number. So if we remove that number, now we have a bunch of numbers that have an even sum because we removed an odd number from an odd sum, so now the sum parity changed. So now the sum is even. We also know the sum isn't 2 because the smallest the sum of at least 2 numbers can be is 1 plus 2, which is 3. And it wouldn't be 3, it would be an even number, so it would be at least 4. So yeah, that's the case. So if you add up all of the numbers, if that number is composite, then that's the answer. If it is instead prime, then you remove the biggest odd number. And that will be, or you remove any odd number, and then the resulting number will be composite. And then that's your answer. So the answer is always either n or n minus 1. And that's how you can do always n or n minus 1. The code for that is pretty simple. Looks like this. Java has this very nice big integer that is probable prime. So we can use that to check. Yeah, this is just an arbitrary constant. I think 30 should be fine. But yeah, this checks if a number is prime. It's not super fast, but in this problem we don't care. I just wanted a quick way of coding it. So yeah, that works. Otherwise, we find OI stands for odd index. So I go through the entire array, and I find the last number that's odd. So I go from 1 to n. If this number is odd, I set the odd index to this. And if the number is prime, that means there will be an odd index. So I don't need to worry about whether this part's true. And then I print it. Okay, that's problem A. Problem B, you have this heavenly tree. So yeah, you have a bunch of constraints, which are this thing can't be on the path between these two. So whenever you're thinking about tree problems, it's helpful to consider the extreme cases. There are 2 extreme types of trees. There's a rope and a snowflake or a star. And in this problem, the snowflake is what you use with the star graph. So basically you have one node in the middle and then a bunch of things coming out from it, which is a very simple tree. Now you're given fewer than n requirements, which means there's some node that will never be in the middle of any requirement. So there is some node where it's allowed to be between every pair of numbers because you're given fewer than n numbers, and there's a pigeonhole principle that proves that. So like if you have 9 requirements of nodes that can't be in the middle and you have 10 nodes, one of those 10 isn't in any of the requirements, obviously. Maybe more than one, but at least one. So you find that node, you put it in the middle, put everything else around it, and now all the requirements are satisfied. It's that simple. Yeah, so don't make a tree like this, make a tree that's a big star. And here, oh, here's what this looks like. I just store a hit for whether it's in the middle. I don't even read the A and C, I just throw them away. So I just get all of the B's that are used, put those in the array, and then I make my center, whichever thing isn't hit, just the last thing that isn't hit. And then I draw edges from everything to the center, and it's that easy. That's the solution. Nice, nice. Okay, on to problem C. You're filled with determination. Oh, this is an Undertale reference. I didn't even read that in the problem. Oh man, oh, that's so good. This is a great contest. Like, let's go upvote it. It's that good. It's so, oh, guys, this contest is so good. Who wrote this? Anton Khan. Oh my goodness, guys, this is a great contest. They did a fantastic job. You guys, it was great. This is one of the best contests I've participated in a very long time. I really like it. The problems are all great. They're interesting. The balance, look at the balance on these problems. Dude, this is perfect. Oh, so good. Okay, I'll stop fanboying about this contest. But this is like global round level quality stuff here. I really like it. Just put some multiplication signs in here. But other than that, this is good. Ooh, good. Okay. Yeah. So, what is this? Oh, we want to know, okay, so you have a grid. A cell is exitable if you can move up and left and get off the grid. Get like off the top or off the side. And the question is, if we're given which cells are exitable, can we determine the grid for a bunch of LR ranges of columns? Now, the key thing to notice here is that if you ever have a cell, let's draw an example here. Let's say you have some cell here where this cell is maybe filled. Like, we don't know whether it's filled, but it's not exitable. What this means is that, like, we don't know. Right? So when is the case that we have a cell that's maybe filled or maybe not, but not exitable? If we have something above it and to its left, then what this means is that, well, you can't exit it, right? You can't go up, you can't go left, so it's not exitable. However, it doesn't matter whether this is an X or an O. You could change it to if it's an X, you can make it an O. If it's an O, you can make it an X. Either way, this will be an X if you look at which cells are exitable. So anytime you have something like this, you have an X above you and X to your left, this is when you're exitable. The one thing, just for completeness, that you also have to consider is, well, is there any other time when this might happen? And there's not. If you have a move, you can just follow that move, right? If you have two moves, you can follow both. But the only time you wouldn't be exitable is if one of these two moves eventually hits this case. So you'll continue just moving in these two directions. It's possible both of these moves don't hit it, right? You might have something like this. So maybe this cell isn't exitable, this cell also isn't. But like, if you are part of the subgrid, then the thing above you is also part of the subgrid. So, you know, you're gonna see, oh, this is invalid anyway when you go to this thing above you. So basically, yeah, the TLDR here is that you want to look for this pattern when you have an X above you and to your left. And if there are any cells that have an X above and to their left that aren't on the leftmost column, then the answer is no, it's not determinable. So yeah, how do you do it? Well, for each cell, you just check, is it one of those things? Does it have an X above it and to its left? And then you have to see which columns have those cells, and then you want to do a range query on the columns. So a great way of doing this is you can store an array that has a 1 or any positive integer. If this column has at least one cell in it that's like illegal, we'll call illegal, it has a thing above it and to its left. So if it has one illegal cell, then we'll mark this column as used. And then for our queries, we need to see, are there anything in this range that has at least one illegal thing. So we can do that with prefix sums. We can do a range sum on the columns. Implementation of that, pretty clean one, I think. Looks like this. Ooh, yeah, that's clean. Beautiful. So we have the board. We read in the board. We store how many illegals are on each X coordinate. And then we start at 1 and start at 1 here, so we can avoid doing out-of-bounds checks. Count how many illegals are on this. So something's illegal if the thing left of it and above it are both X's. and we increment the number of illegals on this column if that's the case. And then we do a cumulative sum on this. So a cumulative sum on, for a range, like for a prefix of columns, in this entire prefix, how many illegal squares are there? So cumulative sum at 0 is for the first 0 columns, so for nothing it's just 0. But cumulative sum at 5 is for columns 0 plus 1 plus 2 plus 3 plus 4. How many illegal squares are there in those 5 columns? So we have how many there are at a given column. This is how you make the cumulative sum array. You do this on paper to convince yourself, but yeah. And then we just do a range sum, and that's it. Okay, cool. Awesome. On to problem D. Meaning of life. Yeah, you have this permutation, which you have to guess, and you have to do some queries. And the queries are, you're given some array, and what the computer is going to do, they know the permutation. They're going to add the ith value to each element in the array, and then they tell you the first index where this element is duplicated. So the first time this thing occurs more than once. So as an example, let's say like the values are 5, or let's say 3, 1, 5, 2, 4. Let's say this is the array, and you give them 1, 1, 3, 2, 4 or something. The numbers you give have to be between 1 and 5, but they don't have to be a permutation like this. So when you add these up, the numbers you get are 4, 2, 8, 4, 8. So the first index which is duplicated, like all of these indices have a duplicate. The first index which is duplicated is this 4. So they would give you position 1. They also tell you position 0 if, or like they give you a 0 if none of the positions are duplicated. Okay, so how do you do this? Well, one thing you can do is, let's say, just for now, we set some position to 0, right? So instead of having a permutation that goes 1 to n, we'll have it go from some negative number to some positive number and hit everything in that range. So we'll not worry about the offset of the permutation until the end, and then we'll fix it so that it goes from 1 to n. We just want the relative order of the elements. So let's pick some element, and then for the rest of the array, this element we pick is going to be the last element in the array, but we'll talk about that later. Then for the rest of the array, we'll calculate what is the thing with an offset of like +1 relative to this element. So we know this element, we know the thing like 1 behind it. So like let's say this is 0. The thing that's 1 bigger than it, well, that'll be a 1. So maybe the 1 is there. The thing that's 2 bigger than it, maybe this is a 2. Maybe we find there's no 3 in the array. So, or there's nothing that's 3 bigger than it. So there is no 3. But what that means is, since we still have like 2 more positions, we know there's a -1 and a -2. So first we'll check -1. Maybe -1 is at this position, and maybe -2 is at this position. So that's what the algorithm looks like. How do we do these queries? Well, for positive numbers, what we can do is we want to find something that's 2 bigger than this, right? So we add 1 to all of these, and if we want something that's 2 bigger than this, we'll add 3 to this. So this will get set to like whatever this is, and then we'll query things +1. So whatever's 2 bigger than this number will be the thing that matches here. So that'll give us this position, because this is the only 2 things that'll match are these 2. Everything else will be different, and then they'll give us the position of this first thing. And the reason everything else will be different is because this is a permutation. So all the numbers are different, and this only matches with one thing, right? Because the rest we're adding the same value to. So we're going to match with the thing that has this offset. So we can figure out where the 2 is by doing this query. And if we want to find -2, we just do the opposite. So we add 3s to all of these, and then 1 to this. And then whatever is 2 less than us is what we'll find here. So finally, once we have this array, we know this is the smallest element, so this should really be 1. So we make this a 1, so we need to add 3 to everything. So we add +3, then we print it with a +3 offset. Yeah, that's the idea. Here is the code. So we have our real array. We search for 1 all the way up to infinity until we find something that doesn't work. And then we search from -1 down to -infinity until we find something that doesn't work. And we fill these into the real array. Then finally we get the smallest thing and add that to everything else. And then add 1 to make it 1 based. So how do we search for something? Well, you just do the exact same query that I mentioned, and then you print it. So question mark, start with a 1, or start with a bunch of 1s for everything else, and then the value you're searching for at the end if you're looking for a positive number. If you're looking for something that's bigger than you. If you're looking for something that's smaller than you, then you add, this makes the x positive because x was negative. So if it's smaller than you, you add to everything else, and then you put a 1 at the end. Cool. Yeah, that's the problem. That's it. Pretty easy once you know the construction, but knowing the construction is, of course, the hard part. Okay, what about problem E? Man, this was such a good set. Ooh, very good set. I did well, but also the problems are just great. Okay. Moment of bloom. What is this? Yeah, this is the one where I asked the dumb question. No. Okay. It's kind of funny, but I like it. All right. So, yeah, this is a good example of how to make a guarantee. This is a very good. This is well done. Well done, problem setters. Well done. This is very good. That's a great red herring. Oh man, just everything about this. They just did a great job. Okay, I'll stop. You guys have heard enough. But this is like maybe one of my favorite Codeforces sets ever. It's just so good. It's so not coding heavy. It's thinking heavy. It's smart. You feel smart when you solve the problems. It's good. I really love it. I think it's great. Geothermal might hate on it because he didn't do well, but it was a good contest. Okay, it was good. All right, how do we do that? What is this problem again? Yeah, this thing where we're given a bunch of paths. So you're given a graph, and you're given a bunch of queries, and each query is a pair of nodes. And you need to say, every time you're given some pair of nodes, you're given a pair of nodes like this. Yeah, so maybe the graph looks like this. Okay, let's draw a graph. Okay, we're given some pair of nodes, so we're given this node and this node. And now we pick some path, and we add 1 to every edge along this path. And now we're given some other pair of nodes. Maybe we're given this one here and this one here. And now we pick possibly some other path, and we add everything, or we add 1 to everything along this path here. And then we're given maybe some other pair of nodes, maybe this one and this one. And we pick a third path and add everything along this path, add 1 to all the edges along this path. And at the end, we want all edges to have an even sum. In this case, all of them do. So these 3 edges all have sum 0, and these 3 edges all have sum of 2. So if they do, you print which paths did you pick to make this the case. And if they don't, instead what you print is how many new paths would you have to add to achieve this. So, oops. I hope that's not legit. I was just told problem F got wrong answer test 5, but I don't think that's true. I think that's my old submission. Yeah, my submissions just got erased because of system testing. So that should be fun. Yeah, so what I was saying here is that if not all of the edges have even degree, if it's not possible to do that, you have to print how many queries do you have to add so that they would. And a proof for what they mentioned in the statement is just that if you just copy all the queries a second time, that would at least make it, everything would be even, right? If you just duplicate everything, it would all be even. So there's a proof that brings it down to n. It turns out, or that brings it down to the number of queries. You can bring it down to like n over 2, worst case, right? Because every query would change 2 nodes. So yeah, so it's at least n over 2. There's another bound. And the right way of doing it is just saying, okay, well, we'll talk about that in just a minute once I mention the solution. So yeah, so it's like how many queries do you need? In this case, it's 1. Right, so you have 1 edge that's odd. You add this query, and now you're good. All right, so first part of the problem, we're given a graph, which is annoying. It would be nicer if we were given a tree, because then we wouldn't have to make any decisions about which path we're adding to. And one can prove that if you have a solution that works on a graph, it will also work on a tree. Why is that? Well, let's say we have some other solution here. Like let's say we use maybe this edge here, and then we use this edge an additional time. If we were to pick some spanning tree, you'll notice we have a cycle here. So we have this cycle. We can get rid of one of the edges in the cycle. So we get rid of this edge, which is fine. But if we get rid of this edge, then it's like, uh-oh, well, now we've done some annoying stuff here. This edge got picked twice. But now, instead of using this edge, we have to use some path. And the path we would use would be this path here. So instead, if we use this path, this, what happens is this edge here would get picked once, and this edge here would get picked again. You'll notice it happens to work, but is that always the case? It is, pretty clearly. Otherwise, my solution would be wrong. And the reason that it's the case is because you're adding an even number to everything along the path. So if everything was even, which of course it was because the graph worked, then it's going to stay even. And you know you're adding an even number because the edges you remove, every time you remove an edge, you add to the path along the tree. Every time you remove the edge, the number of edges that you change is going to be even, right? So if you have some spanning tree and you have some additional edge here that you don't like, what's going to happen is, like if this has a weight of 2, then you're going to change the weights of these by 2. These will all change by 2. They change by even numbers everywhere. And that's your somewhat hand-wavy proof. Okay, so we can just pick an arbitrary spanning tree and do that. Is it necessarily arbitrary? It is. I won't talk about exactly why, but yeah, you can just pick any spanning tree and it'll work. It doesn't have to be the optimal one. And then the question is, well, how do you do it? Well, once you have an arbitrary spanning tree, you can just literally look at the path and then do the BFS, right? You just find the path in linear time. You don't even have to be smart about it. They could have made the problem harder very easily, but it was nice that they didn't because it didn't add anything to the interestingness of the problem by making it small. So yeah, the interesting part of the problem was just like the proof of what we've gotten so far. So basically what you can do specifically is you've got some tree, which you can just make when you have your disjoint set. And you have a bunch of queries which are like range add for this range here, and then maybe like range add for this range here or whatever. So you can just manually modify the degree of all the edges, and then at the end you're left with a bunch of edge weights. So you have something like this. You've got, this has weight 1, this has weight 2, this is weight 2, 1, 1, like that. Now the question is, what do we need to do to change this so that we end up having a even sum on every edge? And the question is more just, where do we need to start and end our queries, right? So it turns out any edge that has an even number, so now we can like ignore any edges with even degree. There's no use going through them. But for edges with odd degree, that means they need to be covered an odd number of times. So for an edge that has, like, maybe it has 2 of these things, well, we know this is going to get covered. We know this is going to get covered, so we can just connect these. So at this edge, we don't have to start or end any queries. But we do have to start or end a query when the number of things entering it doesn't equal the number of things exiting it. So we have to start or end one there. We have to start or end one here. Start or end one here. Start or end one here. These are the nodes that have an odd number of edges with odd degree, or with odd sum. We have 4 edges, but it'll take 2 queries because each query we get to pick any start and any end, and that will be what we're looking for. After that, I mean, I think any start and any end would work. Yeah, it would. That would work. You could do like this, and it just works. But it's not necessarily helpful. Okay. Cool. Yeah, that's the solution. What does the code look like? Code's a little long, but that's fine. So we have a disjoint set. This is how we see which edges are part of the tree and which ones are just other arbitrary edges. We have a list of nodes, and we have all these nodes, blah, blah, blah. These are the edges in the tree. We read them in. We check if this would actually union 2 new things in the component. My union returns true if this would connect 2 different things. So this is what my disjoint set looks like if you aren't familiar with disjoint sets. So this returns true if it actually unions 2 things, or false if they were already connected, which is useful for this exact purpose. Cool, and then we make all of our edges for our tree. This ignores the edges that are part of the graph, but not the tree. So then I store the nodes that are taken in all the queries, and I'll print them out at the end. But yeah, then for each query, I just do a manual BFS, which is really nice because they let us. And I store which nodes are taken in the query, and then I go backwards along the BFS path. So the BFS just stores where everything came from as well, and which edge it took. So yeah, so I go backwards along the path, and then for every edge along this path, I add one to its count. And then finally, I go through all the nodes and see which nodes have an edge that has an odd degree. So I count how many odd degree edges this node has, and then if that number is odd, then I add one to my final answer. Okay, and then yeah, if it's 0, then I print the edges that I took, and if it's non-zero, I just print the number of nodes with an odd number of odd degree edges divided by 2. Like I mentioned earlier, that number will always be even. Proof left as an exercise to you, the viewer. All right, 2 more problems. We're talking about problem F and problem H. Problem F. In one ear, out the other. Solved it, totally forgot. Yeah, you got a bunch of nodes, and you got this K thing. How do you do it? So let me show you. I can show you with the one picture very easily. Here's how. So yeah, we've got some nodes. Let's say K equals 3. We can do something like this. So we've got these nodes here, these 3 here, these 3 here. And what'll happen is we can connect these 2, connect these 2, connect these 2, and then we can connect these 2 like this. And then you can imagine we put these all in like kind of a box here. So we put these in a green box. And then we can have another green box, and then another green box, and we can connect these like this. Which is exactly what we did on these lower layers, right? This was just a red box here. This is a red box, there's a red box, and then we connected the red boxes. And then inside that, we just have yellow boxes. And yeah, very cool. So what you'll notice is the size of each box is 3 to the n, right? So we have 3 to the 0 is the size of the white box, 3 to the 1 is the size of the red box, and we have 3 of these red boxes make a green box. So 3 to the 1 times 3 is 3 to the 2, which is the size of the green box. And then, if you're looking at how to go from one box to another, you just look at the biggest edge you're going to have to use. So if you step from one of these nodes into here, you're going to cross a green edge, so you'll make that green. And the number of times you can decrease by one color before you have to change to another color is equal to the value of that digit, right? So if you imagine going along some path from some number in base 3 to 0, the color of some edge is just decreasing that by decreasing some trit is what it's called, TRIT, some ternary bit, decreasing some trit by 1, and that's one step. So you can do that to but you can only decrease one trit, right? If you want your thing to be illegal, then that means you'd have to decrease one digit 3 times to have a path of length 3, and it has to be the same digit every time. If you ever roll over, like if you go from 2 to 1 to 0, when you try and decrease 0, that'll be a different color because the biggest base 3 digit that'll change will be not the 0 digit. It'll be something else because you'll have to carry over. Okay, hopefully that made sense. But yeah, this is the picture that solves the problem. The code is pretty easy. You can definitely make it easier than what I did. But I represent each number as an int array in base k. And I know this array will be a most size 12 for simplicity reasons. And then you just have to see how do you do this. So I get the number in base k. This is a pretty clear, you should be able to do this if you're solving Div1Fs. Yeah, you just get it in base k. This is the code. You can look at this and think about it if you don't understand how this works, but this is a pretty classic algorithm, base conversion. So once you have the number in base k, this method finds the first, the most significant digit that these two things differ. in base k. So it just literally iterates through all of the digits to see if they differ. And then the answer is when you're going from one edge, or from one thing to another, the color of the edge is, well, you know what you're at, you know what you're going to. It's just the biggest digit that changes. That's just the color of the edge. And it's that easy. Yeah, just print your answer. I did mine, okay, so one thing I should mention is I did my edges from n to 0, n minus 1 to 0, which makes this whole system much easier. The problem calls them 1 to n minus 1, or 1 to n, but you can just, like, the values never matter. So you can just instead pretend that you go from something to something less than you, and you print things out in reverse order. So I just change all the labels and it still works. But yeah, this is actually, if you see it, it's really easy. There are also wrong solutions, which you can work for base 2 and then extrapolate from, but those don't work, obviously. And I spent more time than I should have on this in contest. But oh well, you live and you learn. Okay, finally, problem H. How do you do problem H? So, Akmar and tours. Akmar is hosting tours of this country. Yeah, so you have this, you've got a bunch of queries. Okay. So, the problem is you have a tree where you've got some requirements on these edges, and you've got like some, yeah, let's draw an interesting tree here. Okay. So we have, each edge has like some capacity, and then we're going to do a query where maybe some of the edges are missing, right? All of the edges with a bigger capacity are missing. So yeah, maybe some edges are missing on the tree. And obviously what we'll do is like do a sweep through this where the edges become valid over time, and we'll answer all of our queries offline because we are given our queries offline. So this is for hard problems. This is something you always do. Yeah, so we're gonna answer for, let's say this is the component of the tree that we're interested in. So now what we're asking is, there are some most interesting nodes in this tree. So maybe this node here, and this node here are the most interesting nodes in the tree. Let's make this a bit more complicated. Let's add this here. So maybe these 3 red nodes are the most interesting in the tree. Every node has an interestingness value. And we're going to start on some other node. Maybe we start on this node here. And we're going to take some path to some most interesting node. Which one is not yet determined, but we're going to go to one of the most interesting ones. And we want to know, along that path, what is the maximum value of any edge, where this is like the maximum toll along the edges. So maybe, for instance, maybe we pick to go to this one here, and then we want to pay the max along this path. In fact, what we really want is the max along the paths to any of these 3, because this is what's interesting. That's the amount we're going to have to pay, because we're interested in the worst case. So what we can do to answer that is, if we had the tree that included these 3 nodes, which is this tree here, we want to know the max along this tree, because it's always possible to get any of these nodes in the tree, right? By picking some optimal red node, we can get any of these edges. I mean, we can pay for any of them. Now, it's also possible to pay, if you pick any one of these edges, maybe we pick this one, an arbitrary one. If we look along that path, then what we'll get is this part of the path too. I'll draw it in a different color, maybe green. We get this part of the path too. And this part of the path is the path to this interesting tree. It doesn't matter which one we pick. And in fact, this green path in the solution I'm about to describe will have some overlap. But since we're just taking the max of these, that part doesn't matter. That's not important. So all we need to do is maintain what is this blue tree, and then also be able to answer path maximum queries on some tree, and use some sort of ability to update some path. So we can do this all with HLD. We can also do it with link cut trees. And if we use HLD, we probably also want a disjoint set. Actually, we probably want a disjoint set either way, no matter what we do, because it'll just make things easier. But yeah, that's the idea. So to summarize, we're going to maintain what this blue tree is. To do this, every time we add a new node, because we're doing a sweep here, so anytime a new node gets added to this component, if the new node has a bigger I guess another component will get added, right? So if the new component has a bigger the new component has a bigger, what am I going to say here? A bigger value, a bigger excitingness than anything in our old component, then we delete all of these previous edges. So we undo all of these queries. And we can do this with a segment tree like range subtract 1 with HLD. And this will amortize out because everything gets added once and removed once. So yeah, we store everything we add for a component, and then if we ever need to remove everything, we remove everything. And that will make nodes like uninteresting. And we can store for this blue thing what is the maximum of any edges in this blue tree. We can also store along this path here what is the max for some query. So what we need to maintain is this tree, the max along it, and then for some node, what is its value. And it's that easy. It's possible you don't even need HLD. Yeah, you don't even need HLD, I think. So you can just do this with binary lifting. I think it's that easy. And you just store the max in the blue subtree. You don't even care what it is, just the max. And then an arbitrary node in the blue subtree. And that's it. So a very easy problem H, if I'm understanding it correctly. But I might not be. Or I might have an incorrect solution because I haven't coded it. Yeah, but I think I definitely could have gotten this in contest had I had more time, not spent on a wrong IDNF. Anyway, as I've said numerous times, well, I'm not actually in 15th place, but I did pretty well this contest. My carrot plugin is currently broken, so I don't know what my rating increase will be, but it's going to be, I'm going up. I achieved my goal here, and I did well. And it's pretty early, all before on a regular day I might wake up. So, good day for me. Well, anyway, thank you for watching. Hope you enjoyed the video. Hope you enjoyed the contest as much as I did. And if it was too early for you and you didn't compete, I would definitely recommend VPing this. Now, I guess you've just heard me say the solutions to all but 2 problems, so maybe not. But yeah, if you have friends, there you go. If you have friends, who am I kidding? Programmers, I keep forgetting. If you have acquaintances, fellow competitive programmers, brothers, sisters, cats, dogs, you can tell them they should compete in this contest because it's a good one. And Monaghan helped test it. So that's how you know it's good. Yeah, I already upvoted it, but it's good. It's good. All right, that's all. Thanks for watching. Have a great day, and I'll see you in the next one.